Hello, I'm Antonio. I'm a senior staff engineer at Sonar. I'm leading the Sonar context augmentation project. And we're going to talk about how Sonar does context augmentation for large language models. So here is the agenda. We are first gonna say what is Sonar context augmentation. Then we're gonna talk in general about what is context augmentation for large language models before digging into the details. So how SonarCube does this context augmentation, and we're gonna talk about model context protocol. And the details, so the type of context augmentation that we do, in particular context augmentation for guidelines and for architecture. We're gonna see the tool in action, so how Sonar context augmentation can avoid architectural violation, some results from our internal benchmarking, and then we'll draw conclusions. So, okay, let's start by talking about what is Sonar context augmentation. Is essentially a service which bridge the gap between the coding agents, so such as Claude Code and Cursor, and the user repository. So the idea is that we want to use Sonar analyzers and the analysis, the static analysis of the user to inject information from the local repository, information that cannot be accessed directly by the LLM with the simple tools, and to expand, augment the LLM context with it. And while doing that, we want to maintain the correctness and the speed of the tool. Okay, so some words about what is, in general, context augmentation for LLM. The context is an agent, such as Cursor and Claude Code, and this agent is the one that keeps an LLM context. Because the LLM is stateless, it does not have memory of a conversation. So the LLM context contains the user prompt, so what the user provides when there is a code generation task, and the agent adds to the context information such as the user code or part of it and the environment. And what we want to do is to do augmentation of this context, so provide additional information for the LLM to use when it needs to generate some code. Okay, now SonarCube does context augmentation using MCP tools. In particular, those tools, which are for architecture and for guidelines, take information from SonarQube, information like architectural analysis, the rules from Sonar, and the issues that are generated by the analyzer that detect issues like violations of those rules. And those MCP tools are exposed to the LLM, which then will call the tools when they are needed. So the MCP, the Model Context Protocol, is the mechanism, the delivery mechanism for context that allow the LLM to query for context, ask for context when the context is needed. Okay, just a short description of how the Model Context Protocol works. Essentially, the Model Context Protocol is a protocol that allows the agent to be extended with additional tools on top of the one which are available to the agent by default, and which are exposed by an MCP server. So the agent will start an MCP server and ask for MCP tools. The MCP server will reply with a list of MCP tools, and those MCP tools are added to the LLM context. And during the conversation, the LLM will ask to run some specific tool, depending on the task that the LLM is executing. So the context will be provided on demand, and the agent will receive this request from the LLM, run the tool, which will produce a result, and the result will be added to the conversation so that the LLM can use the information. All right, so now how do we what do we do in those tools for guidelines and architecture? So for guidelines, the goal is to provide some coding standards for security, for quality of the code, and those guidelines should be relevant for the task at hand. So the task that the LLM is executing, and we use two different techniques. We base our guidelines on the user prompt. So, for example, if the user asks to have to implement for the LLM to implement a task that involves access to the database, we include guidelines. So, a rule about bugs, vulnerabilities, code smell about database. And if the LLM plans to modify a specific file, for example, a file called dbstorage.java, then we include the guidelines that comes from past issue on that file specifically. So essentially, we take an historical perspective on the issues, and in using this, we use these two techniques to get guidelines which are relevant to the context, and then we combine them and we augment the context with this information. And now for architecture, we focus on three different areas. We want to help the LLM build the right thing, which means aligning with the user goals and avoiding mistakes while generating the code. Essentially, we want to have less chance of the LLM building code that doesn't work or that doesn't pass the test. And but also we want the LLM to build the thing right, which means we want that the LLM generates code that is in line with the architecture. So if the architect has defined on SonarQube Cloud the intended architecture for the project, we want the LLM to respect this architecture. And the third type of augmentation is about remediation of architectural problems. So when some problem already exists, for example, the code has tangles, has areas where classes are interconnected with each other and it's difficult to separate them, we don't want the LLM to make the situation worse. For this to work, we required a connection to SonarQube Cloud and a recent analysis so that we have architectural analysis on the project. And optionally, the user needs to provide an intended architecture for the project. Okay, so the tool that we provide are for intended architecture, so building the right thing. And actually building the thing right in this case. And building the right thing is about code structure, code flow, and semantic search. So the hierarchy of the project, of a provided class, the references, the code flow, so what is calling what, and then a feature of semantic search, which allow the LLM to search for a specific method or classes or fields by patterns, and these return a fully qualified name of those objects, which are really specific to the code and to the object which is being retrieved. And this is in general more powerful than a text search tool that are provided by default by the LLM, like grep that does a text search, or similar tools that don't understand the differences between overload methods or method in a hierarchy that have the same name but different semantic. Okay, so Here we have a demo of how Sonar Code Context can help to avoid architectural violation in code generation. And we can see that we in this execution of Cursor, we enrich the list of tools with our tools such as get neighbor and get intended architecture. That gives the references and the intended architecture, and the user is asking to perform a certain operation on a class, and this operation requires some architectural changes. So the first things the LLM will do is to use our search tool to look to understand where those objects are located, in particular a class called var_length input stream. And after identifying the object, we will ask for the intended architecture to get the architecture. And then it realizes that the change that it's about to make, it doesn't comply with the intended architecture of the project. So it will propose to the user, because here we are in planning mode, several options to be compliant with the architecture. The user will select one of those options, and the LLM will continue the analysis using more tools, in particular the upstream call flow, to get the dependencies of this particular class. And once it gets a comprehensive picture of what needs to be modified, it will produce a report plan with a list of changes that need to be done to implement the feature, but keep architectural compliancy. And here we can see the steps to perform the change, and at the bottom, the architectural compliance that the LLM respect by looking at the intended architecture. All right, so now some results that we get from internal benchmarking. So by using this tool, we see a better adherence to intended architecture when the architect defines this architecture in SonarQube Cloud. And we also see a slightly better build and test pass rate. So the presence of the tool improves slightly the correctness and the ability of the LLM to come up with code that works. But the biggest improvement we see in performance. There is a 10% stable reduction in cost, tokens, and MCP tool calls, and also reduction in duplicated lines. For complex cases like agentic analysis for vulnerabilities, where the code flow is important and it's not easy to detect with the basic tool, we see a 30% reduction, so a big reduction in token and tool calls. And just to conclude and to recap, so the engineering the prompt is important, but it's not enough to ensure that the quality and security of the generated code is good enough. So we need to go beyond prompt engineering. We need context engineering to get the best result. And Sonar can augment the LLM context with information coming from the analyzers, such as the guidelines to follow while generating code and the architectural constraint to respect. And that leads to a better architecture overall and also a reduced cost. So we don't compromise the performance, and we don't compromise the functionality of the generated code. Thanks for watching.